Good morning, everyone. Welcome to this edition of our monthly meetups, organized as usual by CLIQ-ai, the Computational Linguistics in Quebec Consortium. My name is Fabrizio Gari, and I'll be your host. Today we have two talks around the topic of natural language generation. One is by Ernst, who's going to broach the topic of multi-document summarization. And then we will have the pleasure of welcoming Nicolas Garneau, who is going to present a context where resources are more scarce and which necessitates different strategies. So before we start, as usual, I'm going to ask yourself to mute yourself if you haven't done so that we can enjoy the presentations without any background noise. And in our meetups, usually what we do for the Q&A period is that we allow 10 minutes at the end of each presentation so that you can ask your questions. Your questions can be asked in French or English, and we're going to translate them if necessary. So just note your questions as we go along, and you'll have the opportunity to ask them at the end of the presentation. So if we move on to our first presenter today, Ori Ernst is going to present first. Ori is a postdoc researcher at McGill University and also with Mila. He's under the directorship of Professor Jackie C.K. Chung. He earned his PhD in natural language processing at the University of Bar-Ilan in Israel under the supervision of superstar Professor Ido Dagan and Professor Jacob Goldberger. And his research focuses on multi-document summarization, which is obviously the topic of his presentation today. So if there is, oh, I think that we have background noise. If there is a question, just ask it at the end of Ori's presentation. So Ori, whenever you're ready, the floor is yours. You can start unmuting yourself and sharing your presentation. Thank you so much.
Thank you very much. So I guess you can all see, right?
Perfect.
Great. That's okay. Yeah, thank you very much. My name is Ori Ernst. I'm very honored to be here, and thank you very much for the invitation. And you already represented my background, so thank you very much. Yeah, and I will present this work that was done. Basically, most of it was done during my PhD. And yeah, so let's start. So I guess whenever you have a new task, when you have a problem, you have usually an input data and output data of your main task. The basic thing you will try to do is to train an end-to-end model. Maybe on these days you will take GPT and just like to fine-tune it, as we all know that when you fine-tune it, it's much better than the zero shot. So you'll take it and somehow it would be an end-to-end model, right? You would train or fine-tune your model on your data. But sorry, yeah, sorry, I jumped. Okay, but what happens if the task is too complex and it just doesn't work and it's really frustrating? What can be done? So again, I like to talk about beyond end-to-end. What can be done beyond the end-to-end, beyond training it, fine-tuning it in an end-to-end manner. And I would like to demonstrate it on the case of multi-document summarization, which is quite a complex task, even these days when we have all the large language models, the GPT, etc. So again, to accomplish a difficult task, one must first make it easy. And in order to make a task easy, you can break the task into several subtasks. So let's say we have a main task input and main task output in the red boxes. We can break these tasks into several subtasks, which are easier. We have, for each subtask, we have a model, so we can train this model, the circle model. We have the input and the output of the first easy subtask. And then the output of the first subtask would be the input of the second subtask, etc., until you get your desired output. It looks fine, right? But the problem is, okay, let's say we are doing that. Unfortunately, although we have the data of the red boxes, because this was our task, we have the data of the red boxes, we do not have the data of the blue boxes. How can we train or fine tune all the subtasks, right? Because we don't have the data of the blue boxes. We want. How can we achieve this data? And let's try to show an example of the case of multi-document summarization. So what is multi-document summarization? You have a set of documents on the same topic, and you want to summarize them all together to make a new coherent summary. If you try to do that in an end-to-end model, this end-to-end model needs implicitly to handle several issues. It needs to identify the salient information, to avoid redundancy, so it won't repeat the same information twice in the summary. It needs to take the salient information and to fuse it together to new coherent sentences, and then to plan how to make the full paragraph and generate it. All need to be done in one end-to-end model, which is pretty complex. So although in these days, GPT can do many wonderful things, still, when the input length is very long, it, it struggles to do that. It has some problems. So still, it might be too complex. More specifically, when you want something specific, you want aspect-based summarization. You want some conditions. You give it a long context with instructions of doing it on specific length or in specific aspect or some specific instructions. It is not very good. And when you handle single document summarization, it is much better and much easier. So how can it be done in the multi-document summarization case? We can break the task into subtasks. So we have the input 3 documents. We have the reference summary, the gold reference summary, and we can design the first task of salience detection. We have a salience model that highlights the spans, the salience spans. Okay. After that, we'd like to cluster the spans into semantically similar clusters, meaning that all red spans share the same information. I can use these clusters first to avoid redundancy, to avoid repeating myself in the summary, and it might be a signal for saliency, right? So because if a piece of information is repeated across all documents many times, it might indicate its saliency. So we can use it in both ways. And then we can take each one of the clusters and fuse the information together to a new coherent sentence. So the red cluster would be fused to a red sentence, the green cluster to a green sentence. Because here we have paraphrases in each cluster, paraphrases that share the same information, but each span may add some detail or something like that. So you can fuse them together to a new coherent sentence. And then you take the few sentences and put them into a generative model to produce a new coherent paragraph of summary. And again, we have here the same problem. We do have the input sources. We do have the reference summary, but we do not have salient spans. No one ever annotated for us which spans are which spans from the source are important. No one ever annotated the clusters of the salient spans, and no one ever annotated how to fuse these clusters into sentences. So how can we train or fine tune these? Like, right, we want to train this model and the second model. How can we train this? So let's try to do that. Okay, I will present um, some works that started like it's a long way. It started at Colonel 21. The last paper was just submitted to ACL 24. I represent them all. First, how to obtain training data for the intermediate subtasks. Second, how to use this data to design a new multi-document summarization model, which is state of the art. How to derive then additional standalone datasets, and how to use this method to derive some interesting insights for analysis. So start from the beginning. This paper from Connell 21 won the best paper runner-up, and it looks like it's still relevant. Okay, so again, we have this pipeline, and how can we derive the data for the blue boxes? So let's start with a summary. Here we have a summary sentence, and we can break this summary sentence into pieces, into standalone information unit pieces. We call them, or the term is propositions, right? Let's start reading. Prime Minister Hun Sen insisted that talks take place in Cambodia. This is definitely a standalone information unit. We cannot break it more because if we take only part of it, it would be insufficient. So this is a standalone information unit. And we have another. While opposition leaders Ranarij and Samrenzi fearing arrest at home. And we have another one, while opposition leaders Ranarij and Samrenzi wanted them abroad. So here we break the task, we break the sentence into three pieces, three standalone information units, three propositions. I won't get into the details of the definition of proposition, but just in general, saying that usually centered around a verb and all its arguments. So here we have insisted and all the arguments. But and you can see that the proposition might be not continuous, like in the green case. Okay, now we broke this sentence into pieces, and we can ask, where did the summary information come from? And obviously it came from the document. But where in the document? Here we can see some examples. Here we can see like multi-document summarization. We have three sources. And we can see that the red information came from source A and source B. We have here redundancy. Let's read it a bit. Cambodian leader Hun Sen rejected demands for talks outside the country. So if he rejected demands for talks outside the country, it means that he insisted talks take place in Cambodia. And in source B, it's a quote. All meetings related to Cambodian affairs must be conducted in the Kingdom of Cambodia, Han Sen told. So, we have like, here we have alignment. The alignment between the red information in the summary to the red information in the sources. And we have alignment yellow to yellow, green to green as well. Now let's do some illustration. Okay, here you can see the summary and the sources. We have the alignment with the colors. And I claim that if someone gives us these alignments, we can derive all the data sets we need. So first, I will say that we developed a tool called SuperPal for supervised propositional alignment, which gets summary and documents and extracts all the alignments. Like it gets all blank, black, and colors all the alignments. That's what this tool does. So using this tool, you can derive all the alignments you want. Let's say this tool is perfect. You get the perfect alignments you can have. So let's see how can we derive all the data sets we need. So first, we can derive salience detection dataset. How can we do that? Because all the aligned spans, the aligned propositions from the sources, the summarizer thought they are important. So he or she took them to the summary. It means that all aligned spans from the sources are salient. Another data set is clustering. All the red sources in the all the red spans in the source are aligned to the same red proposition in the summary, meaning they all share the same information. They are all aligned to the same proposition in the summary. So they are all paraphrases of each other. So here we have a cluster of semantically similar spans, green and yellow and blue and as well. So we have clustering dataset. We can also have fusion dataset, where we can take the green and the red clusters to fuse them together to a new coherent sentence which contains the green information and red information. Because the summary, we have green and red. And the yellow would be fused to yellow and blue to blue. So we can design a fusion dataset because we have the clusters and we know their alignments. We know they are aligned to the same sentence. So we can put them at the input and the sentence would be at the output. And that in this case, in this way, we can have this dataset. Overall, we did here some kind of reverse engineering of the summarization process. We revealed what happened during the summarization because the summarizer read the sources and in his or her head thought what are like marked in the head what the salient information is. Clustered the information in order to not repeat yourself, and then fuse them into a coherent sentence. And now what we did here, we just exposed, revealed this process. And now we can use these data sets in order to train our desired model. So the next step would be to create a model. So let's do that. What we did in the pro cluster is like in favor of clustering, which was done in which we talked about in this paper, and also for propositional clustering. I'll talk about it in a minute. So the first step would be break the sources into pieces. We did that with OpenAI, Open Information Extraction. We took it as a black box and we use it to break it to, for us, it's like propositions. And then we used a model to highlight, to find the salient spans. Then we clustered the spans into clusters. Then we ranked the clusters. We used several features, but the main feature was the size of the cluster. You can see here, the larger the cluster, it's ranked higher. Again, if a cluster is larger, it means that the information is repeated more times through the documents. It may indicate that it is more salient. So we ranked the clusters and took only the highest ranked clusters. In this case, we took only the highest three in this illustration, and then we fused them, each one of them to a sentence, red to red, green to green, yellow to yellow. We omitted the blue one because it was ranked lower. And then we just, in this case, we just concatenated the sentences. So you can imagine that this summary is not like, it doesn't connect all the sentences. Like it's not very coherent between sentences. But it's like more like bullet style summary. Okay, so that's what we have done. These two models, the salience detection model and the fusion model, were trained using the derived datasets from SuperPal. We talked about it. We talked about before. The clustering um, method is unsupervised agglomerative clustering, but we adopted SuperPal to measure the proposition similarity. We calculated the similarity between all propositions using SuperPal, which is the same model. I would like to note something about this work and the previous work. Till this work, most, if not all, the work was done in this area was done in the sentence level because it is much easier. A sentence is a well-defined unit. You don't need to think how to break it down. You don't have mistakes when you break it down, or you have less mistakes. Let's say that way. You have less mistakes when you break it down. So people tend to use sentences. However, you can imagine that sentence might be too noisy, right? If you want to decide whether a sentence is salient or not, you have just two options, whether the sentence is salient or not. So in reality, usually what may happen is that part of the sentence is salient and the other part is not. So if you mark it as a salient sentence, you add noise to your system. Again, with clustering, if you want to do the clustering on the sentence level, so many times you take two sentences that part of them is overlapped, but the other part is not. So you add noise to your clustering. That's why we chose to use the proposition level. We break it into the standalone information unit level, which each unit still stands by itself, and then you reduce the amount of noise significantly. I will show that in a minute. Let's see an example. We have here one example, cluster B. You can see this is a cluster of several pieces of information from the sources, and cluster B was fused to this new coherent sentence B. Cluster F was fused to sentence F. You can see I just highlighted here that the fusion model took these words and combined them to these words together. Okay. As I said before, we are state of the art, and I think we still are state of the art in the duck and tuck, as far as I know. We had two versions, an abstractive one, which I presented earlier, and we have an extractive version. I won't get into the details, but it's very, very similar and gets very similar results. And here we outperform significantly all the previous methods. Just to mention that duck and tuck have duck and tuck are summarization datasets in the news domain, and they both have low a very small training data. So I think people moved from they have very high quality. They were they were designed by humans for the purpose of summarization. But people tend to go to the newer data sets were designed more automatically with less with not very high quality and but with larger training data. So here, even though we have less training data, we succeeded to outperform the previous ones. And if we take a look at the Oracle approach, there is still much room for improvement. And also did the human evaluation and got the state-of-the-art results. Now let's go to evaluation. And as I said before, let's take a look in the sentence versus the proposition. If I train only the salience detection model and take the highest ranked sentences and concatenate them together. If I do that in the sentence level, these are the results I get. But if I do it in the proposition level, I get much higher results. So using propositions and improve my model. Then if I add the clustering, how I cluster the salience, the salient spans, and somehow select from each cluster a representative, I get even, I improve my model even more. And if I add the fusion of each clustering, of each cluster, I improve the model even more. So you can see that each part in the pipeline made the improvement. Okay, now we can talk how to leverage the glass box. What do I mean to leverage the glass box? Compared to an end-to-end approach, when you do a decomposed approach, there is a glass box. You can take a look inside the process what happens. You can see through the glass and make this process visible that you can take a look inside have several advantages. Let's take a look at two advantages. First, the clusters are some sort of summary explanations or attributions. So let's say you read your summary and you want to see where this information of sentence A was taken from. So generally, in an end-to-end model, you have to take a look at the summary and start searching, at the source and start searching. Here, you know for sure the information here was taken from cluster A. And if you want, so it can play as an attribution where it was taken from, as a proof. But also, if you want to expand your knowledge about something, you can take a look at cluster A and you can take a look at each sentence in cluster A, see where it came from exactly, and see and take a look at the sentence before, sentence after, and expand your knowledge on a specific uh, uh, piece of information. The second thing is that you can measure summary faithfulness. Let's say you want to measure the faithfulness of this sentence. You need to read the whole multi-document set. Let's say 10 documents. You need to read 10 documents in order to verify this sentence is um, correct, is faithful to the source, and it's impractical. You cannot do that. Like you would have mistakes. It takes too much time. Here, you don't have to take a look at the whole multi-document set. You can take a look only on the specific cluster, cluster E. And specific in this case, we can see that in cluster E, it says Hansen accused him, blah, blah, blah. And here it says the United Nations accused him, blah, blah, blah. So we found a mistake only by taking a look at the cluster. And in practice, we did this annotation and found that 85% of the sentences are faithful. Okay, so let's summarize for now. We revisited the decomposed approach for MDS at the proposition level and with explicit subtasks. The alignment between the summary and the source reveals the fundamental information of the summary. And accordingly, we can derive suitable data sets to various subtasks. Now, we just submitted the paper to ACL 24 to stress the power of the alignment. In the previous papers, we just mentioned that it can do several things, but here we just would like to stress the power of it. So first, we did some manual annotations with over the dataset called multi-news, which is widely used in terms of multi-document summarization. It's a news dataset. We took 100 topics from the test set and annotated them using GUI we developed, using Mechanical Turk with controlled crowdsourcing, which means that we trained the Turkers and then we gave them the task, and it shows like high agreement, and it works pretty well. Overall, you can see here that we have 100 topics for test set, and we have a train and dev set derived automatically by the aligner, by the SuperPal aligner I told you about before. So now we have full data set of alignments, summary source alignments. We have train, dev, and test sets. What can be done with these data sets? So we already showed that we can derive three data sets. But here we would like to emphasize the power of alignment. So I would like to show that we can derive almost any data set we want. So I represented some examples to show the power of alignments in deriving data sets. So we talked about the highlighting data set, the salience detection. Here we talked about a standalone task of highlighting. That if you want to read a paper, you can use this task not only as part of the pipeline for summarization, but also to highlight some sentences that you will read and to pay attention that they are important. So you have the highlighting dataset we talked about before. Here we have the event co-reference dataset or the evidence detection dataset, which in these days people are interested in. Like it's some sort of attribution, right? Where like you have a summary proposition, summary piece of information, where this information comes from. Where this information came from. So here we have a data set. You know the red information is the source of the red summary span, and we can have a data set for this task. All like each color is a new sample. We can have another data set of document retrieval using a query proposition. And here you can see that source B doesn't contain red information. So it extracts only the relevant documents. You can also have sentence composition dataset, which you take, you have all the clusters and you need to group them into groups where each group would be a sentence in the future. So you have to train a model to combine the green and the red information together. This is one thing. Yellow to put alone and blue to put alone. So you need to group them into groups for future sentences. Then we talk about the fusion. We can divide it into two fusion datasets. Fusion of several clusters and a fusion of a single cluster. We can also talk about reference summarization or attributed summarization, where here we can train a model to provide a summary with attributions. Because I have a data set here, which is unique for all summaries, for all sentences and all propositions, I have attribution in the source. I have the reference where from the source this information was taken from. So I can train a model with all these annotations. And I will skip the factor verification one, and we can talk about the information ordering, right? We have clusters, But how can we plan the output, our output? Maybe the green information should be the first, maybe it should be the last. We can train a model. We know for sure that the green information, the green is first, then red, then yellow, then blue. But in the source, we don't know. Here you can see the red was first. Um, you can see the yellow now is first in each document. Like, you don't know which would be first. In a single document, it's pretty easy because you can follow the order in the source. We have a single source. You can follow the order in the source. But in multi-document, you don't know because you don't know, like, this source is completely before this one. You don't know, so you don't know which one you can start with. So by the summary, you know that you can start with the green one, then red, then yellow, and then blue. And you can have that set to filter irrelevant documents at all. So you can see that sometimes you have documents that doesn't contain alignment at all to the summary. It means that they are irrelevant to the summary. So you can use it to filter them out. Here we know, using the alignments, we know that this document is irrelevant to the summary. And finally, a data set for controlled text reduction, which is a paper, a series of papers of this task. This task talks about after we highlighted the desired spend, it might be salient spend or spend that are relevant to our specific aspect, whatever we want. After we highlighted or we marked the spends or the information we need for some reasons, this task focuses on the generation part, how to generate a summary. So basically the input would be the sources with highlights, the output would be a summary or a generative model. Here you can see we have all the tasks and the and to present the power of the alignments. Okay, but what else can be done with these alignments? We can do some analysis. I will skip some of these analysis, but let's take this one. We can see, like in multi-news and on the test set, that there are small clusters, 1.7 propositions from 3 documents on average. So it means that it has low redundancy. And it may say something, maybe redundancy affects summarization or not, we don't know, but we can do this analysis. I will skip this one. I will tell that how the information is spread across documents. I'll tell that 85% of out of the 3 documents have aligning information with a summary. It means that most of the times, one document is not aligned at all. So the information, it doesn't contain any information. It's nice insight. Other insight in the cluster level, that summary span, a single summary span aligns to 53%. Usually it's not aligned to at least 2 documents. So it shows again that there is not much redundancy in this dataset. The orange information is not repeated across documents. Now let's see another analysis and finish with this one. Let's say we have alignments. We expect that we have a summary and we have alignments across the multi-document set, the sparse multi-document set. But sometimes we have the purple information and it just repeats in all the documents, meaning that we don't need all the documents. We can take only one and it would be enough. In fact, we found that in many cases, this is the case. In many datasets, this is the case. You can take only one. It covers 80% of the data. So it's not really multi-document. It's just repeating yourself. Just take the one, take the first one, and that's it. So let's see, how can we do that? How can we know how many documents are required to cover all the information in the summary? So let's create the alignments with SuperPal as we know to do. And then take the first document. We can see it covers, using the alignments, we can see it covers 2 spans. Adding one more, it covers 3. Adding one more, it covers 100%. So the first one covers like 50%, the first two 75%, and the first three 100%. So now we can measure dispersity, right? This document, sorry. So in some cases, the first document is like covers the whole document 100%. So here you can see the coverage while adding documents, how much it covers. So the red curve says that it covers, like taking a single document, it covers 100% of the summary. It means that this topic is not dispersed. So we can measure the area above the curve, but the area above the blue curve is 0. It means it is not dispersed. But the area above the orange curve is something, and the green curve is something else. So it says how quickly can you cover the summary. So we have here a new measure for dispersity, and we measured data sets and show that some of the data sets have really low dispersity, like multi-news, as we talked before, you can see here, really low. And we didn't expect that. And we also made some analysis for summarization systems, how systems tend to, like systems usually focused on a specific document, or maybe they take information from all the documents together, use disperse information. So you can see it in the paper. So to summarize, we took a look on the summary source alignments. We reveal the main properties of the summary. The potential of task decomposition, which can improve the end-to-end one. The potential of new standalone tasks. The potential for analysis using the alignments. So basically, as I said before, the alignments is some sort of the essence of the summarization process. Thank you very much for listening, and I'm happy to take some questions if you have.
Thank you so much for your presentation, Ori. Very interesting. So we have about 10 minutes if you want to ask questions. If you wish to ask questions, you can raise your hand and take the floor. Or if you want, you can just type them in the chat. You can ask your questions in French or English, and we're going to translate for our presenter. So we're going to wait for people to ask questions. I have one, Ori, if you can. You covered the topics of saliency, redundancy, fusion, but for the system that you evaluated against TAC and DUC, you didn't say much about planning and the generation of text. So you covered the topic when you said you showed the many data sets that can be created using your approach, but which one did you use to create the summaries that you eventually evaluated using the TUC and DAC data sets? So I'm really talking about the planning and generation steps.
Yeah, so in fact, in the ProCluster project, where we evaluated against DAC and TAC, we didn't use, like, we took the sentences and just concatenated them. So the summary is more like a bullet style summary. And we didn't use planning and generation and ordering and planning, whatever. We didn't use it. It was left for future work.
Oh, I see. So essentially, it's bullet points, like the highlights that you have at the beginning of an article in The Guardian, for instance, where you have the bullets summarizing the article. But
right.
If I remember correctly, the reference summaries for TUC and DAC are in flowing text. There are no bullets.
Right.
Oh,
and
okay.
and still, people both in the automatic metric and both in the human annotated evaluation, people tend to prefer our system in favor, like more than other systems.
Yeah, yes, it's understandable. So it's the Rouge metric that is used to evaluate?
Right.
Okay.
Right.
Did you try?
Rules for automatic and also human evaluation. Yes.
Okay. Did you try more recent metrics to evaluate, like those that are based on the representation that a transformer or a large language model can give to a whole summary?
No. Because we had human evaluation, we didn't try to add more automatic metrics.
I see. Um, So the approach is very innovative and interesting, especially given the elegance of being to derive so many data sets from the original alignment by SuperPol. My question is, you also make a larger claim, meaning that you could decompose uh, a large end-to-end model, uh, end-to-end process that could be performed by a LLM, for instance, into substeps that could allow you to look inside the glass box and be more efficient, essentially. My question is, in your opinion right now, what kind of NLP tasks could be decomposed the way you did for multi-document summarization? Could we see something like that apply to translation, for instance? And what are your ideas about the decomposition, the subtasks that could be identified for a given NLP task?
Yeah. It's really interesting question. I think that we just in summarization we just followed um, our line of thought, right? Like if we want to summarize a text, what what are we doing? So in fact, I guess that we feel that we trying to trying to find the salient information. We use maybe the redundancy to identify the salient information, and then somehow we fuse it together. So in other approach, for translation, I guess, although I'm not sure, because I guess that like in our minds, what we do is, so it depends like with the um, advanced translator or a very beginner translator, but maybe beginners like translate each word independently in their head, then try to make um, to combine them together, right? And maybe a more advanced one, like when someone that knows the new language that doesn't need to translate like each word, like it translates the whole sentence together. So, but maybe I don't know if it would be better. Maybe translate each word, and then I'm not sure, because in the translation it makes more sense to translate it all together. I don't know. Um, but for other um, um, areas, you can think of question answering. So the first thing you need to do is, like when you have an essay, you have an unseen test, you have a question. So the first thing you need to do basically is to locate where the answer should be. Instead of reading the whole essay from the beginning to end, I guess what you do if you have a question, you just need to find similar words, like you skim the paper and you trying to find where the answer should be. After you extracted the relevant information, then you can ask more specifically about the question, and it would be much easier because you don't have to handle enormous of sentences. You can just extract 10 sentences and find um, the answer in these sentences. So for question answering, it might make sense to break it into extract the relevant sentences, even not that answer the question, just relevant to the query, and then try to answer.
Sure, of course. Yeah. So when you separate a large end-to-end pipeline into subtasks like that, I guess that you're also saving on the number of parameters that you're trying to train. So if you divide the task, you're dividing and conquering essentially, because on the one hand, you could use a large LLM, which is untrainable in normal situations, unless you're Google or Amazon or OpenAI. And you end up with smaller models that you can fine tune independently or retrain on demand. So could you share with us your intuition about the number of parameters that you need on the one hand with a large language model and working with subtasks like that?
So again, it's very interesting. So I don't know like the exact numbers of parameters right now. I need to check, but I think that's why I mentioned that DAC and TAC are have relatively very small training data, and we were able to do that with this amount of training data and to succeed because we did use, like, for the first task of salience detection, we did put as input the whole multi-document, right? Because you put the input the whole multi-document and need to extract salient spans. But we did that with, like, you take the whole multi-document and you mark a specific span. And then you ask a classification task. Is this span salient or not? So the thing is that you get, instead of one instance of a set of multi-document and extract all the spans, you get thousands of instances because each proposition is one instance. And
Yeah,
then you can,
absolutely.
with training data. Training data is 1,000 more, 1,000 times more than the original task. So that's how we succeeded to do that. The other data sets, the other tasks do not, like, the input is not the whole multi-document. Just the first one takes the whole multi-document. And then for the clustering or for the fusion, it's very small. So it's easy. The hard one is the first one. And we did that with, as I said, for each proposition, we have a sentence. We have it's an instance for per proposition.
Sure. Well, Ori, thank you again for your presentation and for answering all these questions. I remind everyone that Ori has published on Superpol, for instance, and we're going to link to add a link to his paper in our event page. Thank you so much again, Ori, for accepting our invitation. And we're going to move on to our next presenter now.
Thank you very much. It was an honor to present.
So our next presenter is Nicolas Garneau. He's a postdoc researcher also at the Coastal NLP group at the University of Copenhagen. He's going to present a talk entitled Guided Beam Search to Improve Generalization in Low Resource Data to Text Generation. Nicolas has several years of experience in software development and data analysis. He specializes in NLP in the legal field. And as a lecturer, he contributes to democratizing AI and has published a lot of scientific works on top of his experience as a postdoc researcher at the University of Copenhagen. So without further ado, Nicolas, you can start your presentation, unmute yourself, and share your screen. Thank you again.
All right, thanks a lot for the introduction. Just let me know if you can see my screen. I'm just gonna Whoops.
It was good.
And then, all right.
Perfect. Perfect.
No, that should be good. All right. Thanks a lot for the introduction. So, as Fabrizio told you, I'm going to talk about guided beam search in the data to text generation setup. So what's on the menu today? I will briefly introduce what data to text generation is, the data set that we are working on, which is a legal French data set, the human evaluation that we conducted on 3 neural architectures, and finally, I will introduce the guided beam search that we presented at INLG last year. So data to text generation is usually we talk about like normalized data to text. So we could have like text to text generation, image to text generation, but then the data to text generation scheme, we talk about like normalized data where we would call that maybe table of values, where we have different values that we want to verbalize and produce some sort of description out of it. So in our setup, we are talking about generating court dockets descriptions, which is a legal document really central to the legal system here in Quebec. And we want to use these neural networks to generate these descriptions. So we basically, this is some work that I've been doing during my PhD with CLIQ-ai and at the University of Laval. And so what we wanted to test is how far can we get with neural networks in a very low resource setup. So that was the basic idea. So this is one of the last paper that we published around that topic. So just to get a bit up to speed with what the data is. So on the left side here, we have what we call the docket file. This is basically just the first page of the docket. Docket files usually are spanning pages long. And so the first step in this project was to basically take this first page and try to generate a description out of it. So as we can see, we have a lot of information in that first page that is somehow normalized, but we still use an information extraction model to further normalize it and extract the bits that are important to us, such as the accused name, the plaintiff name, the number of charges, and what the charges are. So we have the number referring to the criminal code. So we have, for example, 2 charges here around provision 733.1 and 430, which I'll introduce a bit later. So the basic idea is to take these documents, we perform some sort of extraction out of it, and given that normalized view of that document, so we just like we put it in the table of values, extracted the different values. And what we want to do is to generate that sort of description where John Doe pleaded guilty to a failure to comply with an order and a mischief on property on October 1st, 2015, basically. So that's pretty straightforward. So we try to gather different informations and produce that description. So in its really raw form, the docket file will look like this, but what we do is that we extract every provision from the Canadian government website containing the criminal code, and we will further contextualize the generation with this, because otherwise just providing numbers to a generator is pretty useless. So we contextualize, we had the label of the provision, mischief, and oftentimes there's paragraphs that will further complement the inputs. So the data set that we're working with, we have around 1,000 training examples. That's the data set that I created a couple of years ago, which we called Plume to Text, which is actually a set of input values from docket files that and that translates into a description. So we have basically 1,000 training examples and roughly 400 test examples. So that's why we're sort of in a like low resource setup. We're working on the legal field. We have not many training examples, and also furthermore, we're in French, so we don't have at that time, we didn't have access to the LLMs and stuff, so it was a bit harder to provide meaningful descriptions out of this document. So this is a concrete example from the data set. So as I said, we have table of values. For example, in this case, we have 3 values. One is the accusation, referring to provision 320.14, which is impaired driving under the effect of alcohol or drug. This is the most common offense in Canada, obviously. And we have a plea, so the accused person pled not guilty, was declared guilty. And then we have an associated reference where a given person pleaded not guilty on account of impaired driving and was declared guilty. So in this data set, I manually removed every name, every contextual information that could provide some sort of re-anonymization of the person, because we wanted to first make it as clean as possible so that we don't have noise, that we don't have the name of the persons, which somehow helps a bit when we're in a low resource setup. And also it's for a matter of privacy, of course. So this is the kind of reference that we have associated with this kind of tables here. So we have conducted a manual evaluation around the generations of several neural networks because they're, at that time and even now, they're still known to omit or hallucinate facts. And we really wanted to have like a clear picture of how good or how bad they are at using this data set for training and testing as well. So what we did with F. Gaumont, which is, well, now she was a student at Laval University. Now she's now a PhD at Montreal. She's in the Faculty of Law. I sat with her and we designed this sort of legal accuracy scale, which is bounded from 1 to 10. 10 is a perfect generation, and 6 to 9, we have the good provision that has been verbalized by the model. 2 to 5 is a similar provision. I will get back to this. What's a similar provision? What's a good provision in a few seconds. And if the model is just completely off track, when the model is not able to generalize on unseen provisions, most of the time it's going to be completely off track due to the nature of the data and the scale of it as well. So what we defined was what we call the theme. What's the theme? It's basically the fact that some provisions share some similar concepts. For example, we might have trafficking in substance, and we also have the provision possession of for the purpose of trafficking, which we sort of define as similar provisions. Whereas driving under the influence is not similar as trafficking substance. So this is what we call the theme. So we have a bunch of provisions like that in the criminal code that are related to each other. And this is what we're going to use to position ourselves on the scale. So the idea is that if we have the good provision, the good provision is generated by the model, we're going to be in the green part. Like we have a good generation. We're just looking for factual errors at that point. If we have a similar provision, for example, the value in the table was the accusation was trafficking in substance, but the model for some reason generated possession for the purpose of trafficking. Well, we consider this as a similar provision, and then we were going to sit between the 2 and 5, and then we're just going to look for factual errors at that point. And if we're completely off track, for example, we had as input trafficking in substance, then the model generated the most common infraction, which is driving under the influence. Then we ask the annotator to just assign a score of 1, which is completely off track. And at that point, we just don't look for factual errors. This is just a bad generation. So in terms of factual errors, what we call the precision of the generation, we look for hallucinations, which we define as anything that is not supported by the input table. And also omissions, which are table values that haven't been verbalized by the model. And then we just ask the annotator that for every hallucination, every omission, we remove points on the scale. up to a limit of, for example, if we had a good provision, up to a limit of 6. If we had a similar provision, up to a limit of 2, for example. So we trained 3 models with different priors. The first one was the LSTM that we trained from scratch. So no prior, we started from scratch, training on the 1,000 examples and evaluating on the 400 on the test set. We also use Barthez, which is a French version of BART, which at that point we have the language prior in a sense. And we also used CLIQ-ai, which is a model that we proposed a couple of years ago at ICAI, the International Conference on AI and Law, which is the Barthez model, but we train it on the large corpus of legal judgments from the Canadian court in French. So at that point, we have both the language and the domain prior. So we wanted to see how the prior impacts as well on the generalization. And this is without a surprise that kernel bar will have like the better performance, but we wanted to see like how important that is. So we recruited 2 other students in the Faculty of Law. So Hev was performing the evaluation manually, as well as 2 other students. And we gave them basically the legal accuracy scale with a document presenting how we presented data, how we gathered data, how the models generated this, just to have a primer on what to expect and what we call basically the annotation guidelines. And so we used Prodigy, the web application, to perform the evaluation. So as an input, we had the table of values. So for example, here we have provision 348, which is breaking and entering. We have the plea and the decision. And then we shuffle the models so that we don't have the same models, so that people don't get biased by the generations. And we just ask the people to input a value between 1 and 10, according to the legal accuracy scale for the different models. And so from previous research from André Ducek, he also conducted a similar way of evaluating multiple models so that we present them all together instead of just one generation, so that we can also somehow rank a bit the generation if we are not really sure what's better or not, or what's really really bad and what's really good. So these are the results on the human evaluation that has been conducted. So without any surprise, kernel-bar was better than both Barthez and the LSTM. And of course, the LSTM is really poor at generalizing because it has only seen very few examples, training from scratch. So of course, that's a really, really helpful setup. But still, we still have a bit of work to do for kernel-bar. We still have a lot of instances where the model is completely off track, predicting the most common accusation, the most common infraction. And we also want to move these bits a bit towards the green part so that we generate the good provision, but maybe with some factual errors. So these are the results per annotator. So as we can see again, kernel-bar is very good. But what I want to show here is that even though the generation and the task per se can be quite ambiguous for some people, is that like, is the provision on theme or not? Given the annotation guidelines that we provided to the students and the sort of legal prior that they had, the annotators had quite a high agreement nonetheless. So at that point, once we've done the human evaluation, what we realize is that generalization is quite poor on unseen provisions, even for kernel-bar, which is not really able to handle unseen or new law that could have been proposed. So this is exactly where we want to boost a bit more the numbers, and this is where the guided bin search will come in. So, for example, we have this quite rare provision, which is 3041, which is attack on premises, residence, or transport of an internationally protected person. This provision does not happen really often. We might have one training example in the data set, for example, or one in the test set. So it's quite understandable that with so less data, Kinnet-Barton would have a hard time to just deal with that provision. So, for example, here, so we still have something on team, but all the annotators agree that this was completely off track. But Kinnet-Barton tried to generate something that the person exercised assault and battery against a person, which is somehow related, but still we're quite off track here. So the idea is to better leverage this input and try to make something out of it, so that the generation is maybe a little bit less confident, but we're exploring a little bit more the generation tree. So the idea is to at any given step try to re-rank a bit the scores and try to, because like this assault and battery, for example, is again one of the most common accusation in the data set or in Canada in general. So we'd like to maybe explore a bit more the decision tree and generate maybe a less confident generation, but could potentially be more on point. So the work in that last paper was based on a very cool idea that we borrowed from HiFace, a system presented in 2017, which from a person I don't want to like completely butcher his name or her name, but this work was I think was very cool, very simple. The idea is very neat. And the idea is just to apply either penalty or a reward, as we would call it, on the score or on the beam score. So like a beam at every time step has a score, and that has been accumulated over time. And then when the model is generating like next word, we just take the probability or the log prob of that next word, we add it to the beam score, and then we just continuing generation and so on. So what HiFace did is that given a set of functions with respect to that next word that should be generated, we're gonna either add a reward or add a penalty on that next word so that we can move a bit the probability distribution and maybe explore more wisely the beam space, the different beams. So what we did is that we replaced this term here with a very simple term. We have what we'd call a reward of omissions and a penalty of hallucination. That is both, these are both weighted by gamma, by omega and gamma here. And so the idea is that the less value we omit from the input, the more we get a reward out of it. So the more we verbalize the table, the more we get a reward. And the more we hallucinate fact, or the less we hallucinate fact, we can see both ways. The more we hallucinate fact, we'll get a higher penalty. So the idea is to not hallucinate, so that we don't subtract scores here. So O of I and H of I here are basically floats or integer. Usually we could see them as integer because it's a number of hallucination, number of omissions. But we use a regressor to train the model on the data that I will present. So these are basically floats. So just as a technical point. And then we just add this to that current beam score so that we get a new beam score given that next word that we're trying to generate, so that we can, as I said, try to explore a bit more in a wisely manner the search space. So as I said, omission reward and destination penalty. So in order to get these two values, the omission reward and the hallucination penalty, we created two models. One that predicts the number of omissions and another that predicts the number of hallucinations given the set of values that we have as an input and the sequence that has been generated so far. So in an ideal world, we would have a data set that has like sequence generate, like a start of sequence generated, and then we can train the model on how many omissions or hallucinations there is or there are, but we don't have access to this. So we created some sort of proxy training data set, which I think sort of kind of does its job at some point. So we created a new training data set from the original 1,000 training examples. So from the original training example, where we had the actual table values, we have the accusation, plea, and decision, for example, and a reference. We label this example as having 0 omissions and 0 hallucinations. And that's pretty obvious because that's the training data, right? And then what we do is that we pair every example in a training set that has some sort of overlap, and then we're going to sample those that don't have an overlap, because there's a lot of examples that don't have an overlap between their respective table. So here, for example, we have 2 examples, 2 instances. First instance, table 1, reference 1, and the second one, table 2, reference 2. What we do is that we take the table from the first instance, and we're going to pair it with the second reference. Conversely, we're going to take the second table and we're going to pair it with the first reference. And this is going to create ourselves what I call the proxy data set, so that we can train the omission model and the hallucination model. If we take this one, we have the provision 3 2014, plea not guilty and declared guilty. And table 2, we have a different provision. We don't have a plea. Sometimes we don't have a plea in the table, and we have declared guilty. So the overlap is on the decision. So if we pair this table of values with that reference, we have a given person is accused on account of assaulting another one because of this provision by applying force intentionally and was declared guilty. So we will have 2 omitted values. Provision 3 2014 with respect on that reference, with respect to this table, we will have 2 omissions, so the guilty plea and the provision. And we will have hallucinated provision 265 because it is associated to that table. However, there's nothing regarding the decision because both are declared guilty. And we do the same thing with table 2, paired with reference 1, where we happen to have omitted 265. We hallucinated 320 and a guilty plea, for example. And this there's a small error in the example, but it's a not guilty plea. So we have this new training data set that is a proxy of what is going on when we're doing the beam search. I know, but we have this training data set where we can somehow have these models, the omission reward and the hallucination penalty model. And so we train this on the data set, and the model was able to obtain a really high performance. If I recall correctly, we used, I think, SentenceBERT or something like that to train the model. So we have very low MSE, high accuracy on the number of hallucination and omissions that have been detected by the models. So now we have a way to compute these values at every time step during the beam search. So what we did is we perform an automatic evaluation as it is always required when doing generation. I know it's not really faithful to what we're expecting, but still we have the blue scores, Rouge, Meteor, Bird score as well, NLI, and rank, which is a metric that we proposed a couple of years ago at NLP as well. And so in every cases, when we were applying the reward or penalty, we slightly improved the beam search. So this was using a grid search. We used the best possible values for the beam when using no penalty, no reward. And it turns out that if we grow a bit the beam search size and then we apply reward and penalty, we're having better results at that point. So improvements look a bit marginal here, but I think what's more interesting is the human evaluation. So again, we gathered 45 unseen provisions from the criminal code. So that is not in a test set, not in a training set. And we again asked the same 3 students from the Faculty of Law to evaluate these generation again with the evaluation guidelines that we provided, as well as the legal accuracy scale. But it was basically the same experiment that we conducted with in the previous paper, but on very targeted provisions. So these are all the provisions that we gathered. And as we can see, the original criminal bar is able to perform quite like somehow it's able to generalize, but most of the time we're either using similar provision or we're quite off track. And when we're using the guided beam search, we are able to improve substantially the generations, but still we still had some places where the generation did fail. And there was one interesting case where the generation got worse. We didn't look into much detail on why did that happen. Just that the exploration of the beam was maybe a bit confusing for the model, and then we ended up with a worse generation at that point. But still, improvement. We went from on average 3.9 on the legal accuracy scale to 7.4, which was very, very exciting. So if I take back the previous example that I showed, we went from exercise an assault and battery, which is a very common infraction in Canada, to the average score given by the 3 annotators on 8.33, which exercise an attack against official premises, a person enjoying international protection, and blah blah blah. So the actual provision is not the good one; it's 341, but we are on the right provision. We're talking about the good stuff. So this is just a simple example of the actual steps in the beam. So what's very interesting that we can properly analyze what's going on at every time step, and the reward and the hallucination that we get. So in that specific example, the model, this is the prediction of the model in both cases. In this case, obviously the reward and the penalty has not been applied. And in this case, and using that beam, the reward and the hallucination penalty has been applied, and then we end up with a generation that where the model was predicting here no emissions and no hallucinations almost, and on the other side we still have emission and hallucination. And finally, we also applied this to WebLG, just to sort of confirm that this method is sort of generalizable to other data sets and other domain. I agree, WebLG is quite a easy data set nowadays, but still, We just wanted to prove our point that we can still create this artificial data set. We take the instances from WebLG, pair them together, so we can create this omission and hallucination data set to train a model. And then we applied it again on WebLG using either the reward and penalty or not. And in every cases, using automatic evaluation metric, it did improve, or it did not degraded the results, at least. We did not conduct a manual evaluation because time constraint and resources, but still we have a good idea on how what's the improvement here on this data set. So conclusion, guided beam search show that we're able to better explore the generation tree. And also what's really interesting is that predicting the number of omissions and hallucinations at a given time step sort of offer interpretability for free, as well as guiding the model. Granted, these predictions are not 100% accurate, but still we get an idea of what's going on at every time step. Thanks a lot, everybody, for having me. And if you have any question, please just feel free. If you want to write me an email afterwards, it's also very welcome.
Thank you so much, Nicolas. Quite interesting. We have about 5 minutes for questions. So I see that Professor Guy Lapalme has a question for you. Guy, just unmute yourself if it's not already done. And then...
Félicitations, Nicolas, pour cette présentation. C'est très astucieux, ton système. Ben, j'aimerais revenir sur le truc sur les dockets, là. Je n'ai pas trop compris quelles étaient les données. Est-ce que le système a juste le docket ou a aussi la description associée au numéro ou des
On a aussi la description. On a aussi la description associée au numéro. Donc, on va avoir vraiment là, accès à ce bout de texte-là. On n'a pas juste le numéro de l'accusation, comme je l'avais présenté là, au tout début. Là.
OK.
Donc, on a accès vraiment à ça aussi. Hein.
OK.
Puis, je ne sais pas où tu vas aller avec cette question-là, mais je pense que, en fait, un des projets, c'était de voir à quel point on est capable un peu de combiner ces accusations-là, puis d'en faire ce que j'appelle un peu un one-liner. Puis bon, le travail est en collaboration avec la CLIQ, qui détient ces dockets-là. Puis en fait, la conclusion moi, que j'avais à la fin de mon PhD, c'était si on veut vraiment contextualiser, puis parce que le but ici, c'est vraiment comme d'offrir un peu un niveau d'interprétation pour les citoyens. De ce document-là, parce que ça ne parle pas à grand monde, puis de dire, bon, ben, on va essayer de le contextualiser, puis d'ajouter une petite saveur un peu plus légère. Ce que j'ai conclu, en fait, ce que j'ai proposé à la CLIQ, c'est de dire, bon, ben, utilisons pas un réseau de neurones pour venir générer une description, venons juste contextualiser, prenons les accusations directement du code criminel, venons contextualiser ça, ça va déjà offrir un pas de plus vers une interprétation du document. En fait, moi, si c'était mon chapeau, si je mettais mon chapeau d'ingénieur, c'est ce que je ferais. Je n'utiliserais pas un réseau de neurones pour venir générer une description qui potentiellement pourrait contenir des omissions, des hallucinations. Juste aller contextualiser les accusations avec ce qui est écrit sur le site web du gouvernement du Canada. Pour moi, c'est good enough. D'un point de vue recherche, je pense que c'était quand même pertinent de voir est-ce qu'on est capable jusqu'où on est capable d'aller avec un réseau de neurones pour combiner toutes ces valeurs-là.
OK, merci. C'était un peu l'impression que j'avais. C'était un cas facile vous n'avez pas comparé avec un système bêtement symbolique, là?
Non, on ne l'a pas comparé. Puis, en fait, je pense qu'il faudrait peut-être poser le problème d'une façon peut-être un peu différente, parce que, comme tu vois ici, on a l'accusation 430-1A, où est-ce qu'on va dire, bon, ben, mischief, everyone commits mischief who willfully destroy or damages property. Tu sais, le cas facile, cas symbolique, ben, c'est juste de prendre, bon, ben, je vais aller chercher libellé mischief. Paragraphe 1, everyone commits mischief. Alinéa A, destroys a damaged property. Je vais coller tout ça ensemble, puis ça va être la description de mon docket. C'est le modèle le plus facile. Il y a un petit peu de redondance. Des fois, les paragraphes, que c'est un peu plus verbeux. Cette accusation-là est assez succincte, mais des fois, c'est plus verbeux. Puis je pense qu'on serait plus dans un cas de summarization ou un cas de simplification textuelle. Où est-ce que là, je pense qu'on aurait une petite translation au niveau de la tâche, là, mais je pense que si on le positionnerait comme ça peut être intéressant aussi.
Surtout que ça aurait été facile à faire. C'est pour ça que je me demandais.
Effectivement.
C'est-à-dire, c'est plus simple à utiliser ça que beaucoup des métriques, que les packages de métriques automatiques. Ça fait que je trouvais ça surprenant que vous ne l'ayez pas essayé. Ben, ceci dit, le restant de la présentation qui utilisait ces données-là, ben, l'autre astuce, je l'apprécie beaucoup. Félicitations. Merci.
Merci beaucoup, Guy.
Merci, Nicolas. Il y a une question dans le chat. Non, pardon, je me suis trompé. C'est une ancienne question pour Ori.
Oui.
So, Nicolas, I'm going to ask this question in English. If there are no other questions in the audience. So my question is, since you're using transformers, essentially criminel BART, which seems to perform quite well with your beam search, why not enforce the rules of hallucination and emission by adding two attention heads, one for the provision and the other one for the guilty or not guilty plea? Would it not achieve the same result with less complexity?
I think it would be a very great idea to test out. I think the only concern I would have is the training data that we have to train these attention heads, because maybe I did not say it explicitly, but we use kernel BART as is. We didn't. Well, we trained it on the data set, on the training set of the Plume to text data set, but the beams, like the reward and penalty on the beam search is sort of a second step, so that we don't need to retrain other parameters. But I agree that it would maybe do the same thing using attention heads as having this fancy penalty and reward stuff.
Yes, and at the very least, it's very, very astute to add this beam search on top of the decoding step. Do we have any additional question in the audience? I think that maybe Jianyun would like to say something.
Okay, thank you. So I find the idea to generate some new cases with hallucination or omission, that's very interesting, and that reminds me the idea of trying to identify hard negatives or construct the hard negatives, and this is kind of a similar idea. And when you suppose that you construct a case with hallucination that you generated, can you use that as a hard negative in the training process? And in that case, you will not have a different model. You would try to integrate that into the training process. So would that work as well, in your opinion?
I think it could work, but I'm not sure exactly how you would use the R negative in a generation process. How you like, because when you're training, given the input table values and you have the associated reference, what you mean is that we could have table of values where they're with their sort of hard negative references, and I'm not sure exactly how we could train the model to like not generate these stuff, or just or we just penalize it in a generation scheme, for example.
Yeah, well, in the case of contrastive learning, so suppose that you have a positive example, trying to generate something and to not generating some other thing. And in that case, you will have two generation stories, and what you want is to maximize the first probability and minimize the second one. So you will have some contrast in two generation probability, so that you will make the contrast between a good example and a bad example.
Sure, and that contrastive loss would be every time step, right? Just like a normal CE loss, right?
Yeah. So this is just using that contrastive loss to replace the just generative probability. So when you have a positive example, you want to generate a positive example to maximize that probability.
Yeah.
But when you have a contrastive learning, you will maximize one probability and minimize the other one. So you will make some contrast.
Sure. I think that's a really great idea, and that could be like very cool experiments to conduct in the, and I would be super excited to do this.
Thank you. I think that generation of those additional data, this is really very interesting, and I will try to think whether this idea can be used for some other tasks that.
Of course. Of course, yeah. I also like a lot the idea, and it's quite simple. You just like use your own training data set, and you try to, given what you have in hand, you try to derive some other stuff. A bit like Ori did with his own data set, which I think it's a bit clever than just annotating more data and more data and more data.
Yeah. And one interesting thing, both of you presented some tasks, related tasks, but you use very different approaches. So that both of you come back to that contrast of approaches. So Ori used the description by proposition, and then using cluster and so on to try to get salient facts from a cluster, and then try to summarize. So this is I would say this is a more traditional methods that we may have in mind. And of course, when human beings try to summarize, we do that kind of thing. But one thing that one question I had in mind is how likely that we will create a good proposition. That is a kind of understanding of text. When you transform a text or a sentence into a proposition, the accuracy may be a problem. Which is the basis of your whole approach, right? So if there is some mistake or some flexibility that you can observe in the conversion into proposition, then the following steps will suffer from that. Do you see any problem from that, Ori? Or how would you look at that problem?
Yeah, so I guess the question is for me.
Yes.
So we evaluated it, and we found that, I won't get into the specific metric, but we found that we lose 10% of our accuracy. Like our upper bound by using OpenAE is 90% of, let's say accuracy without getting into the details. So so we lose information, but it's still much better than use the full sentence. And you're right, maybe for some cases we need to go even like it's a bit hard to define what we want. So we took the case of propositions, and it's a bit hard to extract propositions automatically. Maybe it can be improved, but you can imagine that you may need some other levels of breaking the sentence. Let's say you want to evaluate faithfulness. The proposition level might be too large. Maybe you want a specific argument. Maybe I told I went to school yesterday, and in the summary it says I went to school 2 days ago. So we want just the argument part. So you need to break it even more, and then you have to do that. So yeah, it's an issue, but yeah, you need to handle it.
Yeah. I read some papers that are trying to associate or to combine the traditional logic with neural machine learning stuff. So there may be some place where you can transform your proposition that you get into a neural form, so that when you have similar propositions, you will be able to compare them. Because otherwise, when you represent in a symbolic way, then you have to choose your symbols to your words to represent them, and the proposition or the same statements can be described in different words in different documents, and that will make them very difficult to be compared. But once you convert them into some embedding form of representation, there may be some possibility to compare similar statements.
So if I understand correctly, what the question is, I think that our superpole model, just that what it does, it takes the proposition, convert it to an embedding, and calculate the similarity to another proposition. That's how he makes the alignment between the summary proposition and the source proposition.
Yeah. Okay. Right. Good. Thank you.
Thank you for the question.
Well, I think Jianyun has had the last word.
Yeah.
So
Thank you for your.
it was really a pleasure to welcome you both today. Thank you so much for accepting our invitation. I think we're going to conclude on this. As always, I'd like to thank my collaborators, of course, Jianyun Yi, who's the lead researcher for our consortium, and my collaborators at Ivado, Mariam Tagmouti and Nancy Laramé. This presentation is being recorded, so you're going to be to see a recording of this appear on our website. We're going to add some links to some of the papers that have been mentioned here, especially the Superpole for Ori, and we'd like to add a link to the paper on guided summarization from Nicolas. So I guess that what remains is to thank everyone for attending this meetup. I hope you enjoyed the presentations, and stay tuned for more news about the upcoming meetup. So I look forward to seeing you, all of you, next time. Until then, have a pleasant day, pleasant weekend. Bye-bye.
Yeah. Thank you. Bye-bye.
Thank you.
Thank you. Bye.